A very good morning to one and all present here, especially our resource person, Dr. Bele Damodara Shenoy, respected father, principal, Dr. Benike John C.S. Holy Cross College, Agartala, respected vice principal, Father Joe Paul, Holy Cross College, Agartala, all the respected faculty members and my dear students, a very good morning and warm welcome in this workshop, today's workshop. And the Holy Cross College, Department of Human Physiology, today we gather here in collaboration with MicroAsia uh, s- on this international workshop on the topic of introduction to bioinformatics. And today's topic of discussion is the molecular phylogenetic analysis. Today we are having a resource person, Dr. Shenoy. He is the principal scientist of the CSIR, National Institute of Oceanography, Visakhapatnam, Andhra Pradesh. So, and we started our journey and we planned this workshop, organize this kind of workshop in collaboration with MicroAsia just 20 days ago, and we received huge response from the various participants from various countries. Even we have so many international participants also in this workshop, and they are participating today's workshop. So till now, we received 1,520 numbers of registration, and we'll accommodate as much as possible today's workshop. And with these few words, I'd like to call upon our father principal, Dr. Benike John CSC, to deliver his welcome address and to start our this today's workshop. Over to father. Yes, father. Yes, father.
A very good morning, maybe good afternoon, and good evening too, as we are participants from all over the world. It is my privilege and delight to extend a warm welcome to all of you to this workshop, an international workshop on bioinformatics organized by the Department of Human Physiology, Holy Cross College, in collaboration with MicroAsia. And I am delighted to see large number of participants registered. As I am told, it is even around 1,500 or so, comprising of scientists, research scholars, teachers, and students from all over the world. Truly shows the significance and the importance of the topic that we are going to discuss. On my part, I acknowledge and appreciate the department and especially our principal resource person, Dr. Belle Damodara Shenoy, for your efforts, for your time and goodwill to share knowledge and to have a network with one another. We are in academia. Thank you, sir, very much for your time and cooperation with us and with our department. On my part, once again, I extend a warm welcome to all the participants for your time, for your collaboration, and networking with one another in sharing and caring and learning from each other. I wish you everyone a good time at this workshop and all the best. Thank you, one and all.
Thank you so much, respected father. Now, in this, I want to introduce a little bit about this workshop. Today we are having two sessions. One is first session is this is the lecture session through which we'll be able to understand the basic bioinformatics, basic tools related to the bioinformatics, and after that we'll start the hands-on training. So with this, in this regard, I would like to hand over the whole session to our resource person, Dr. Shenoy. So over to you, sir. Just you can start your this technical session.
Thank
Now,
you,
over
Dr.
to sir.
Thank you, Dr. Susmita Saha. Am I audible?
Yes, sir. You are audible.
And I would like to thank the principal of the college for giving me this opportunity and for operating with MycoAsia for this an important international workshop on molecular phylogenetics. Okay, good morning, ladies and gentlemen. Maybe early good morning in Africa now, maybe late evening in the US or North America. How is everyone doing?
We all are good, I think. Sir.
Good morning, sir. We all are good. Just waiting for your session.
Yeah, thank you so much. I mean, I thought let me just do some kind of ice breaking before I get into the.
Sure, sir.
Thank you. I'll just mute all of you. Maybe if you have any queries in between, you can type in the chat box or raise your hand, and during the appropriate time, I will let you speak then. Is that okay with all of you?
Yes, sir.
Okay, great. As you know, we have been talking about this workshop for last 20 days. I hope I'm audible. Am I clear?
Yes, sir. Yes, sir. Audible.
Yes, sir.
Audible, sir.
Okay.
Yes, sir.
Okay. Thank you. Thank you. Yeah. My name is Belle Damodar Shenoy. I'm from India, and I work for a government research institute, which is situated on the east coast of India. First of all, I would like to thank the Holy Cross College, Agartala, Tripura, India, for collaborating with MycoAsia and giving this wonderful opportunity to me and MycoAsia to share our ideas on molecular phylogenetic analysis. Some bit of me, some more information about me. As I told you, I work for a research institute. The research institute is, the name of the research institute is CSIR, National Institute of Oceanography. I work in the regional center, Visakhapatnam, which is on the east coast of India. I am presently a principal scientist, and I am also a co-founder and managing editor of a new mycology journal, MycoAsia. So this is my email address. These are my email address, and this is my mobile number with the WhatsApp account. So this is the website of my parent organization, CSIR, Council of Scientific and Industrial Research. It is an autonomous body under Ministry of Science and Technology of the Government of India. The Prime Minister of India is the President of Council of Scientific and Industrial Research. This is the website of my organization, National Institute of Oceanography. Our main office is in Goa. We have 3 regional centers, 2 on the west coast, one in Mumbai, another in Kochi, and 1 regional center on the east coast, which is in Visakhapatnam. And we do multidisciplinary research, ranging from physical oceanography, biological oceanography, chemical oceanography, marine engineering, marine instrumentation. So if you are interested in oceanography, please visit our website, www.nio.org. I'm very glad we are collaborating with Holy Cross College, one of the top colleges of India, and as per the NAAC, it is one of the best colleges with the A+ grade. I'm very thankful to Dr. Susmita Saha and Dr. Sarkar and Father for the collaboration once again. Yeah, thank you. I would like to talk about MycoAsia. It's a very new journal in the sense we are trying to connect with the interested people, and we want to collaborate with the people for the promotion of mycology, promotion of open access mycology. So we are a non-profit organization in that sense. Please visit our website, www.mycoasia.org. You can find our recent publications. You can get information about upcoming events and the past events. Okay, if you are interested in joining MycoAsia network, you can go to this tab and just submit your information. So coming to today's plan or today's workshop, what is the plan? I mean, today is Monday, 8th May 2023. The workshop will be up to 13 hours Indian Standard Time. That would be GMT plus 5 kind of hours. What is the plan like? As I told you in the WhatsApp group, first I will be giving a presentation maybe for 45 minutes. Then I'll be inviting questions. You are welcome to ask questions in between, but it would be nice. It would be very organized, I would say, if we can just restrict our questions to, or restrict our questions to maybe some at the segment, at the end of some segments, I believe. After the presentation and the question and answer session, we will take a break maybe for 5 or 10 minutes or maximum 15 minutes. Once you come back from the break, I will demonstrate about NCBI GenBank, how to download and install Mega software, lastly, how to download and install RacksML GUI software and play with these softwares. Actually, and I will show you how to make phylogenetic trees using these Mega and RacksML softwares. Once I am done with the demonstration, we can have one more round of discussion. You people, you keep your questions ready and keep your comments ready. And at the end of this workshop, I will share a link where using that link you can give the feedback about feedback on this workshop, especially on molecular phylogenetic analysis. We hope to finish this workshop by 1 p.m. Indian Standard Time. It should be okay, I guess. We should be able to do that. First of all, I would like to give credit to the source of information from I have taken most of the information from this book chapter by Michael Webb and Marcus Goker. Chapter 12 of one of the books, Molecular Phylogenetic Reconstruction. In the book The East, actually, which was published in 2011. So, as you know, the title of the workshop is molecular phylogenetic analytics. So what is phylogenetics, or for that matter, what is phylogeny? Okay, that is an important question. Phylogeny is nothing but evolutionary relationships of organism and genes. So here the basic idea is that the proteins and genes which are present in our body acts as evolutionary chronometers. Using these chronometers, we can measure the evolutionary change. This is a very important thing. As you know, we have proteins and genes. All living organisms have proteins and genes inside them. But where do you get this information? Where can we get DNA and protein data? If not ourselves, or if not ourselves, maybe the DNA and protein data of the bacteria that you're working with in the lab, or the fungi, maybe other organisms you're working in the lab. Basically, you can generate DNA sequence data, protein sequence data of the interest from an organism of interest in your lab itself. So in the case of fungi, you actually collect, for example, a soil sample, isolate the fungi, select one of the fungi, extract DNA, then amplify one of the gene regions, maybe ITS, then you sequence that region, and then you would be happy to generate such sequences in your lab. But don't worry if you are a beginner, if you have not generated gene sequences yet. You can go to one of the important public online databases, NCBI, and do some good. You have some good fun there, actually. So the important question is how to retrieve information from NCBI GenBank. Actually, there are two ways by which you can get DNA sequences and protein sequences from. First you can use a keyword search. Keyword search is like Google search. Instead of Google, you go to NCBI GenBank, and here is the nucleotide option. Here you type, for example, Aspergillus niger. So then you will get the relevant information. If you have your own sequence, then you can use a tool called BLAST. Using the BLAST tool, you can get homologous sequences from the database. So basically, there are two ways by which you can get information from GenBank. Okay, well, first one is through keyword search. Second one is through BLAST. Okay. So if you have a DNA sequence data, for example, what can you do with DNA sequence data? You can do many things using DNA sequence data. But one of the important things, what I have been doing is to construct phylogenetic trees using DNA sequence data. You can construct phylogenetic trees using protein sequence data also, but my expertise or my experience has been with only DNA sequence data. So therefore, I'll be focusing on only DNA sequence data and phylogenetic tree construction using such DNA sequence information. The important question is, what is a phylogenetic tree? So what is a phylogenetic tree? I mean, you might have, of course, you know natural trees, which has a root and which has leaves, which has branches. Similar to a natural organic tree, we can also have a phylogenetic tree. So this is a phylogenetic tree, where you have the oldest species or oldest groups of oldest species group, or as a root here, then you have other life forms. Okay. Basically, it is a phylogenetic tree. It's a phylogenetic tree is nothing but an estimate of the relationships among taxa or sequences and their hypothetical common ancestors. Okay. So if you are from taxonomic background, you would know the meaning of the word taxa. Taxa is plural. Taxon is singular. Basically, taxon means taxonomic category. Taxa means taxonomic categories, the plural. Basically, we are talking about the evolutionary, estimating the relationships among the taxa of your interest. For example, if you're interested in fungi, you'll be interested in estimating the relationships among some fungi. For example, Aspergillus. If you're into bacteria, you would be interested to know the evolutionary relationships of some bacteria, maybe Escherichia coli or Pseudomonas. So it's so you want to understand the relationship of the presently extant species and their hypothetical common ancestors. Why it is hypothetical? Because for many things we don't have data. So then we hypothesize. So evolutionary studies mostly about the hypothesis that way, actually. And phylogenetic tree construction, the idea of phylogenetic trees is not just new. I mean, it's not very new. Phylogenetic idea of phylogenetic tree was there during the time of Charles Darwin. This is the picture of phylogenetic tree, kind of a tree drawn by Charles Darwin. This is from a page of Charles Darwin's notebook. Okay, so now I'm talking about 1880, 1860, 86, 1870s or 90s actually. Now we are in 2023. So when in 1978 we had this idea of we found the evidence for the three-domain life actually, including bacteria, archaea, and eukaryote. That was based on ribosomal RNA actually. So this is also a phylogenetic tree. So this is a beautiful tree that picture of it, a very beautiful tree that I shared in the WhatsApp group recently. It's the tree of macrofungi. It's very beautiful, but you don't find this kind of trees, phylogenetic trees, in all the publications. In the publications you can find this kind of tree. Very simplified tree. This is a phylogenetic tree of the kingdom of fungi. Presented by Hibbett et al. 2006. Actually, it changed the way we perceive the fungal taxonomy. Okay, where some of the groups like Zygomycota or no more. Chytridomycota are used in a very restricted sense, and the Microsporidia has been considered as a part of a kingdom fungi. So this is a very oversimplified kind of phylogenetic tree. I will tell you why it is an oversimplified tree later on. But this is a typical tree, phylogenetic tree you find in a research publication. So this tree is very interesting because this is talking about the identification of penicillium culture, which was used by Alexander Fleming to produce penicillin. So basically, here is the ATS or beta tubulin sequence from the Fleming's penicillin producing culture. Okay, so all the sequences this sequence is clustering with the other members of Penicillium rubens. Basically, it is identified that Fleming's penicillin producing culture is Penicillium rubens. It is not Chrysogenum or So this is the beauty of phylogenetic analysis. You can place the fungus or organism in a correct context, in a correct place on the phylogenetic tree actually. So this is the morphology of Fleming's penicillin producing penicillium culture. Now you might ask me, how to construct a phylogenetic tree. You have seen different kinds of trees. I mean, not different kinds of. You have seen examples of phylogenetic trees. So you might ask me, how to construct a phylogenetic tree. I mean, there are 4 important steps in the phylogenetic tree construction. First one is assembling a data set. If you have your own sequences, I mean, you're in the sense the sequences generated in your lab. It could be ITS sequence of a fungus, a 16S rRNA gene sequence of a bacterium, or it could be Cytochromoctridase 1 from an maybe butterfly or okay. Then you have your own sequences, or you have your own sequence. You get homologous sequences from the public databases like GenBank. Maybe use BLAST or you use keyword search or okay. Once you have a data set, you have to do multiple sequence alignment. That is the second step. Why in the multiple sequence alignment, more than 2 sequences are aligned and the homology of these characters are tested and confirmed. Once there is a very valid multiple sequence alignment, you can find the best trees based on certain assumption and hypothesis actually. Then this will result in phylogenetic trees, a tree or trees. The branching pattern has to be tested for this statistical support. That testing we do using a method called bootstrapping actually. So I'm coming back to the same for all those 4 steps. First step is assembling a data set. Second one is multiple sequence alignment. Third one is finding out the best trees using the multiple sequence alignment. Last one would be doing the bootstrapping to find out the reliability of the branching. Okay, I'll be explaining all these things in the coming slides. So now here is an exercise for you. You have to identify different parts of a phylogenetic tree and tell the meaning of this. So maybe one of you can just tell me different parts of a phylogenetic tree. Any volunteer, please? Am I audible?
Yes, yes.
Any volunteer who can identify different parts of a phylogenetic tree? Okay, fine. If there are no volunteers, let me explain. Because this is an important slide. A phylogenetic tree has basically two parts. First one is nodes, and second one is branch. Okay, I'll explain this, and you can also have a root. Okay. So node, there are 2 kinds of nodes. Those could be terminal nodes, which represent the existing extant species, presently living species, or the sequences you are using in the analysis. And there are internal nodes. This is an internal node, for example, that this internal node represents the hypothetical ancestor of these terminal nodes. Okay, there are two kinds of nodes: terminal nodes and internal nodes. Okay, terminal nodes or leaves or tips, they represent the extant species or the sequences that you use in the analysis. And the internal nodes on a phylogenetic tree actually represent hypothetical ancestors. For example, this is an internal node, and this is an hypothetical ancestor of these sequences or terminal nodes. The second important part of a phylogenetic tree is a branch or branches. I mean, there would be many branches. So basically, this is a branch. I mean, for example, here it's a branch. It's a straight line. Okay, it determines the ancestor relationship. For example, for example, here you find two sequences. Okay, and this should be the branch which connects to the hypothetical ancestor. Okay, so the branching pattern of a phylogenetic tree is called topology. Okay, this is a topology. How the branches are separating, that is called topology. So this is an important term. So the branches can have different length actually. So what we call branch length can be of different size actually. Longer the branch length, longer a branch actually, that means greater amount of evolution might have happened, in that particular group. So now there is a phylogenetic tree, so we can root a tree actually. So what is meant by rooting a tree actually? Basically one of the nodes would be the oldest ancestral species. So using that particular node, we can root the tree. What is the benefit of rooting a tree? When you root a tree, you get the information on direction of evolution. For example, in this very illustrative tree, actually, we have, archaea kind of a primitive organism as the root of life, actually, on Earth. So that gives an idea about the direction of evolution. So therefore, we can root a phylogenetic tree to understand the direction of evolution. Then how to actually root a tree? You can use some sequences, what we call outgroup sequences, outgroup species, to root a tree actually. In this case, this is an outgroup for all the organisms here. If you are studying only about human beings, then the fish can be an outgroup. If you are studying human beings and fishes, actually, then I think plants can be the outgroup. So what are main features of an outgroup or outgroups? An outgroup or outgroups should not belong to the group of interest, your interest. If you are studying Aspergillus niger, then Aspergillus fumigatus can be in an outgroup actually. Okay, so an outgroup should be phylogenetically separate, but it should not be very distant. When you are studying humans, you should probably not use archaea as the outgroup, because we are very far from the archaea, on the phylogenetic tree. So that will not help in the alignment, multiple sequence alignment. So when you look at a phylogenetic tree, you should focus on two things actually. You should look at the branching pattern, how the sequences are separating, that is topology. And also you also look at the branch lengths, that will give an idea about the amount of evolutionary change between taxa. For example, here the Penicillium confertum looks like evolved faster than the other one because it has a longer branching. Just giving an example. So what is a phylogram? Phylogram is just a graphical representation of a phylogenetic tree. Here you have information about the branching pattern and the branch length also there. Comparatively, what is a dendrogram? Dendrogram shows only the branching pattern. There is no information about the branch lengths. This is a typical representation of dendrogram actually. So you can see probably for an experienced eye, there is a difference actually. For a beginner, I'm not sure, you might struggle to find the difference here. This is a phylogram and this is a dendrogram actually. Here, information on branching or the topology and the branch length is there. Here, only the branching pattern is represented. Branch lengths are not represented. See, any questions? Any questions? No? No?
Hello,
Yes.
am I audible?
Yes, sir.
So, in what instances do we use the cladogram and the dendrogram?
See, when people were using only morphological characters, they use dendrogram. Okay. Nowadays, not many people use dendrogram. And if you are interested in the branch length, amount of evolution that might have taken, then phylogram is must. Any other question? Hello? No?
Just a second. So basically, the dendrogram is just going to tell us about the relationships, and the phylogram is going to give us the evolutionary picture, right?
No, both will give an idea about evolution. There's no doubt about the evolutionary relationships. In the dendrogram, you have only branching pattern. Okay, but in a phylogram, you have branching pattern also plus branch length information. Amount of evolution that might have occurred in each group of organ, each group or each lineage in that phylogenetic tree.
Probably difference in depiction pattern, probably, sir. Q.
Sorry?
Probably difference in depiction pattern.
Basically that one actually, yes. When you see molecular phylogenetic studies started with cladistics. Cladistics was basically using morphological characters, to find out the evolutionary relation. Then the dendrogram was very dominant. Later on, because of development of analytical tools, you can not only find out the branching patterns, you can also give information about the amount of evolution that might have occurred in the form of branch lengths. Okay, can I continue?
Hello.
Yes, ma'am.
Sir, I have a question. Could you please focus on the slide where you have shown the branching length or branches? Actually, I want to know exactly where are the nodes in this in this tree. Where are the nodes exactly, and where are the internodes? How can we say?
Okay, that's a very good question. Normally, what kind of goals are the round thing as nodes are not represented in a typical phylogenetic tree in a research paper. Okay, so here all these sequences are terminal nodes here.
Okay.
So they are not shown in the form of rounds or circles. Okay, but these are terminal nodes. So these, for example, here, can you focus on these two?
Yes, sir. I can see this.
Here, the place where this particular branch is, separating this particular near the 99.
Yeah.
This is supposed to be an internal node, supposed to be the hypothetical ancestor of these two taxa.
Okay.
So that's a very good question, the question actually.
Yes, sir. And these both, which has been branched further. So these are the terminal nodes, right?
Yes, these are terminal nodes. Basically, terminal nodes are nothing but extent species. Extent species. When I say extent species, the sequences that we use in a phylogenetic analysis.
Okay.
Because we mostly use the sequences from the living organism at the moment. Actually, fossil data information is very scarce.
Okay, sir. Fine. Thank you, sir. That's clear.
Any question? Any more question? Yeah. It's good to have questions in between because otherwise people will sleep and I will also not knowing whether you understood or not. Yes, ma'am.
Excuse me, sir. Please, can you go to the same slide, sir?
Yes.
The terminal nodes, this top one, they are not represented with any length of the line. So that means, what does that represents like?
If you are talking about this particular
Yeah.
branch,
Yes,
yeah,
sir.
they are almost those sequences are almost identical or very similar.
That means they have evolved at the same time with the. I'm not getting the meaning of what this represents.
We are talking about the 6 sequences. Actually.
Yeah.
Okay? For example, so they are, in my understanding, 100% identical, or it could be around 98% to 100% identical. There is not much difference in terms of their sequence composition.
Okay.
If they were different, you would see the branch lengths differing. And they are the same species, right? And I think it's the beta table.
Okay.
Ma'am, in general, you can say the base patterns are same. Base
Okay.
patterns are same.
Okay.
Okay. So,
Okay, sir. Thank you.
did you ask Salim?
Sir, please
explain
proceed.
this?
Okay.
Okay, let me proceed now. I think keep your questions ready. Hello? Mallikarjun? Yes.
Some
Hello?
of the participants are very new to this kind of dendrogram and cladogram. Sir, if you explain how branching is taking place and how species are related, you explain a little bit more in deeper. That will be more understanding to the new persons.
That's fine. You wait for the demonstration. Some of the things will be clarified during the demonstration.
Sure.
Okay. And as participants, don't talk unnecessarily, making lots of noise. Then I have to mute everybody. Okay, but I don't like to mute everybody. That will actually affect the expression of the people. Fine. Thank you. Anyway, coming back to where I think I was somewhere near. Okay, some issues actually. Now, what will happen? Let me talk about a couple of issues in phylogenetic tree construction. First of all, what will happen if you have only 10 sequences in a phylogenetic analysis? What will happen if you have 20 sequences? What will happen if you have 50 sequences? So, if you have 10 sequences, that will result in 3, 4, 4, 5, 9, 4, 2, 5 distinct topologies. So if there are 10 sequences, there would be many this many number of distinct topologies. When you have 20 sequences, you just read the number. That many numbers of distinct topologies will be generated. Topologies means branching patterns. Okay. When you have 50 sequences, you would have 2.75292 into 10 to the power 76 distinct topologies. There will be so many branching patterns, distinct branching patterns, as you keep on adding more sequences to the file. So that means it will become more complex for a phylogenetic software, analysis software. Then how do we deal with so many distinct topologies? Then we use optimality criteria. So basically, optimality criteria deals with how to get an kind of, you make an average of something actually. For example, when you do the strict consensus tree, for basically, two ways of optimizing phylogenetic trees. Basically, when you have so many distinct topologies, the first approach would be have a strict consensus tree approach, where you will generate a tree that will have those groups that are represented in all source trees or all the topologies. That is a strict consensus tree. Okay, that is the first one. It's a strict consensus tree, where you consider so many distinct topologies, thousands of them, millions of them. Then you come with an average kind of a tree, where you consider only lineages or branches that are present in all the source trees. That is strict consensus tree. Second one would be majority rule consensus tree. Then in this tree, that will contain only the groups that are contained in more than 50% of the source trees. So one is very strict, those branches should be present in all the source trees. That is strict consensus tree. Second one is majority rule consensus tree, where if you find these branches in more than 50% of the source trees, then it would be considered in the final tree actually. So basically, this is about optimizing these phylogenetic trees when you have so many distinct topologies because of the complexity of adding so many sequences. Actually. So as you know, you need more than 2 sequences for a multiple sequence alignment. So this is a pictorial representation of a multiple sequence alignment. So each column is considered as each column here is considered as a character. And the difference in the nucleotide here, for example, how do I say? Here A and G are there. These are character states. Okay, and all these nucleotides are believed to be homologous actually. Basically, multiple sequence alignment is nothing but the estimation of homology of nucleotides between the sequences. Multiple sequence alignment is more important than the tree building methods, because as you know, you can add any sequence and get a phylogenetic tree. You might use the most sophisticated tree building method, but if the sequences you use are not relevant or of poor quality, that resulting tree will be a garbage. Remember the computer world, the phrase from the computer world: garbage in is garbage out. So this multiple sequence alignment is more important than the tree building methods. So better to exclude ambiguously aligned characters. That these things we will understand when we do the through the demonstration. There are 2 major tree building methods. First one is distance matrix methods. These are also known as clustering methods, algorithmic methods actually. For example, neighbor joining and UPGMA, these come under distance matrix methods. Second one is discrete data methods. These are also known as character-based methods and or tree searching methods. So what we commonly call as parsimony, maximum likely Bayesian methods. These all come under discrete data methods or character. What is the major difference between distance matrix methods and the discrete data methods? This is a little bit confusing. Just for the simplification, I am showing here. In case of distance matrix methods, multiple sequence alignment is first converted into a data matrix. Then the data matrix is used to construct a phylogenetic tree. That is a distance matrix method. In case of discrete data methods, the phylogenetic multiple sequence alignment is used as it is, and it is used to construct the phylogenetic tree without the involvement of data matrix generation actually. Okay, so I'm just explaining this again. There are 2 major tree building methods: distance matrix methods and discrete data methods. Neighbor joining comes under distance matrix. UPGMA also comes under distance matrix. And under discrete data methods, you have parsimony, maximum likelihood, and Bayesian. So what is the major difference between distance matrix and discrete data methods? In the distance matrix methods, say, for example, neighbor joining, UPGMA, where the multiple sequence alignment is converted into data matrix, and that data matrix is used to construct the phylogenetic. In the discrete data methods, including parsimony, maximum likelihood, Bayesian analysis, the multiple sequence alignment is used as it is, and the phylogenetic tree is constructed. There is no involvement of data matrix, step actually. There are some important features of distance matrix methods. For example, neighbor joining, UPGMA. Basically, here the data matrix is converted into phylogenetic tree. Okay, these distance matrix methods are applied, for large data sets. It's because they are fast enough. They have reasonable accuracy. For example, neighbor joining. But that is not the end of phylogenetic analysis, because they have reasonable accuracy. Therefore, you need to opt for a more accurate methods, such as maximum likelihood Bayesian or maximum parsimony, for example. So the distance matrix methods like neighbor joining can be a good starting point. I was mentioning about distance matrix, in this step, distance matrix. So how do we estimate the genetic distances? Basically, these are some basic information. P distance, one of the oldest formula. Here the P is equal to number of different nucleotides divided by sequence length. So this actually underestimates the actual number of substitution. Therefore, other genetic methods are distance calculation methods are there, which actually account for the hidden or multiple substitutions. Duke's Cantor distance is another method, and Kimura 2 parameter is another one. So when we do phylogenetic analysis, we use DNA substitution models, especially in maximum likelihood, and maximum parsimony, and Mr. Bayes. So we have Bayesian analysis, substitution models. The question is how to decide which method is good for phylogenetic tree, whether distance or discrete. Good question. We'll come back to this. Actually later. Okay. Thank you for that question. Let me continue. So what are DNA substitution methods? These DNA substitution models, actually, there are some important questions. Whether the substitution rates vary across alignment sites. If they vary, then we use gamma distribution. How about the base frequencies, whether they are constant over time? And how about the base composition, whether they vary at different points in the tree? So these are the complicated sounding questions DNA substitution models actually ask actually. And the UPGMA is the simplest form of a distance matrix tree. It's a straightforward approach. Okay, the full form of UPGMA is unweighted pair group method with arithmetic mean. So it's a very old 1958. It's a straightforward method and it results in a rooted tree. Okay. Actually, there are some unreasonable assumptions. It assumes that there is a constant substitution rate over time and phylogenetic linear basis. This assumption is often violated. Therefore, UPGMA is now rarely used. But a neighbor joining, another distance matrix based tree building method, is very often used because it's fast to use and it gives a rough idea about the branching and also the branch length. Okay, how to estimate the branch length? Branching pattern is good, but you need to have information about branch lengths. How long is the length? How much amount of evolution might have taken place? So basically, it is possible. It has been done. So there is something called least square approach, which is used by the statistician to estimate the branch length. Actually, so as I was talking, we could have so many number of topologies, distinct topologies. So we need to use optimality criteria. So these are the optimality criteria. For example, Cavalli, this is one of them. This is the second one. So these are the optimality criteria commonly used in phylogenetic analysis. So this actually reduces our burden of, and identifies some trees which actually represents so many distinct topologies. So the important question is, what is a neighbor joining tree? So it's an improved version of what we call minimum evolution criterion. As I told you, it's a very fast method, and it is used for large analysis. I mean, it's used for the analysis of large data sets. Okay, and it's a distance matrix method actually. Then what is maximum parsimony tree? It is a tree building method under discrete data. No, not a distance method, discrete data. So it's one of the oldest methods, parsimony methods. So these parsimony methods are developed from cladistics analysis of morphological characters. This is as old as 1965. So when researchers were using morphological data for the evolutionary analysis, so these cladistics parsimony actually was developed. It was developed initially for the morphological characters. Now the maximum parsimony is, not now, and in 1971 for nucleotides and amino acid parsimony algorithm was introduced. Basically, in maximum parsimony, the software, the algorithm actually finds the topologies which explain the distribution of observed character states more parsimony. Basically, it means you have a multiple sequence alignment. It will consider the alignment in such a way that only minimal evolution. It creates a phylogenetic tree with an assumption that evolution is very stingy and evolution is kind of slow. Therefore, evolution is parsimonious. Just Google the word parsimonious. Basically, it means stingy. So the tree generation is based on the concept of parsimony or stinginess of the evolution. So this is just a diagrammatic representation where it gives an idea. For example, this is from the main source I am citing from. It gives an idea if there are minimum number of changes in our substitutions, that kind of topologies will be considered by the maximum parsimony. So then moving towards the probabilistic methods of phylogeneity. What are these? So these are actually probabilistic methods. For example, these methods include maximum likelihood, Bayesian. These come under probabilistic methods. These are the phylogenetic methods which use the probabilistic theory and statistics. So these more into statistics, highly statistics intensive, and they make assumptions about DNA substitution. They use DNA substitution models in analysis. Maximum likelihood is one of the important, probabilistic methods of phylogenetic inference. What is maximum likelihood method actually? Basically, it looks at the multiple sequence alignment, and actually it finds a tree which has the highest probability of giving that kind of branching. So this is more about probability, likelihood of having that kind of branching pattern under a set of hypotheses. It's also statistically intensive, but this is one of the most successful approaches. So one of the substitution models uses GTR, that is called general time reversible substitution model. In Mega, you can use this very easily. This is the statistical information about general time reversible. It's reversible DNA substitution model. There are other DNA substitution models, for example, Duke Cantor, F81, K2B, HKY, K3S, TRN, SYM, GTR. So these are used in phylogenetic tree construction to get an idea about DNA substitutions. So what is happening in the data set? What might have happened in the evolution? How do you know which substitution model is the best? There are two ways of doing it. One is you can do a likelihood ratio test. It's a common statistical approach where it will tell which model will be the best. Second one is IK information criterion. If you use this criterion, the software will tell which model would be the best for the given data set actually. So basically there is one more statistical analysis. So tree building, tree making analysis, that is Bayesian analysis. It comes under probabilistic method, and it comes under actually discrete data. So Bayesian analysis is based on the Mr. Bayes formula, Bayes formula, not Mr. Bayes. Bayes formula. It's this is the statistical information. I'm not going to get into the statistics part. So in the Bayesian analysis, what we use Markov chain Monte Carlo approach. So by this you get millions of trees, then you can shortlist the trees actually based on certain statistical hypothesis, certain statistical consideration. So you have a branching pattern. Then how do you know whether the branching pattern is statistically supported? For that, do bootstrapping. So in bootstrapping, you take random subsamples. From random subsamples, you build trees. Then you calculate the frequency of occurrence of different parts of the tree. Take random subsample. For you have multiple sequence alignment. You have 500 characters or columns. So you take random subsamples. From each subsample, you build a tree. Then compare the phylogenetic tree from each subsample or random sample. Then you calculate the frequency of occurrence of different parts of the tree actually. So this is the bootstrapping is the test of phylogenetic accuracy of the tree. Basically, these are the bootstrap values represented in percentage. If the bootstrap values are more than 70%, it is believed to be good actually in terms of reliable groupings. So you have a tree, raw kind of tree given by the phylogenetic analysis programs like Mega. You might like to edit some of the things. For example, make sure branch lengths are drawn to scale. Okay, they are drawn, and you give the scale bar here also. Then bootstrap value should be displayed as percentages here. And normally bootstrap values lower than 50% are not reported. Actually, you're not shown on a phylogenetic tree in a publication. And you can choose to root a tree, phylogenetic tree. When you root a tree, it gives information about the direction of evolution. With this, I complete the presentation. Now we can have a discussion for 15 minutes. Let me just unmute you, all of you. Yes.
Thank you so much, sir. Am I audible?
Yes.
So I hope it was an just introductory part of this session. Is it? Or we are going to discuss in detail in this at 11:30?
At 11:30, I'm gonna show demonstrate certain things. I know how to retrieve sequences from GenBank for beginners. Then how to download Mega and construct phylogenetic trees, and also download MaxML. Then download and install and generate maximum likelihood trees. These are the things I'm gonna cover in between 11:30 to 12:30.
Okay. So my question is this, like, how to make the data matrix. You have shown like once we make the distance matrix, if we are using distance matrix method, then we have to make a data matrix. Then how to make that? And there are so many questions like what is the use of estimating branch length?
Okay,
what is the importance of it?
One question at a time. First one,
how to make the data matrix.
You don't have to do anything. You get the sequences, then tell the program to create a multiple sequence alignment. Okay. When you choose distance matrix methods such as neighbor joining, the program itself converts the multiple sequence alignment to a data matrix, and that data matrix will be used by the program to construct a phylogenetic. It happens if the data set is very small. All these things happen in 5 or 10 minutes. You don't have to do. You don't have to. These are very simple things to do actually. Nothing much to worry about.
Okay, fine, sir. And sir, I'm expecting like we will be get demonstration on the like how to use the different methods like neighbor joining, maximum parsimony, all the things like in the
I
your
think,
data set or
yeah,
any presentations.
it's very easy to do all those things because in Mega you have all these options. You
Okay.
know, you can create on multiple sequence alignment. Then you can choose which method you want to use. All that can be done in Mega. Just wait for the demonstration.
Okay, sir. Okay, thank you so much, sir.
Some of these things will be clarified then.
Okay, sir. Thank you so much, sir. That's all.
Thank you. Any other questions?
Hi, sir. My name is Nimsi. Sir, I have. Can you hear, sir?
Yes, please.
Sir, my question is, while we constructing some phylogenetic tree, some organisms that appear very closely related may not actually be closely related. So, why is this happen, sir?
I think it depends upon your taxon sampling, basically.
Sir, one more question, sir. By selecting the outgroup, sir, while we creating the fungal phylogenetic tree, can we consider bacteria as a outgroup, or we consider any other fungal group as an outgroup?
It depends upon your research question. If you are talking about the evolution of fungi as a whole, and you are using a suitable marker, a suitable molecular data, then probably you can use prokaryotes as an outgroup. Yes.
Sir, one more question.
And if you are focusing only at the genus level or at the family level, maybe the closest another family can be used an outgroup.
Okay. So one more question. While we considering the phylogenetic tree, we see that there is internode distance 100, 90, 73 in your branching slides, sir. So is it has any significance?
Yes, I was explaining in the presentation. Maybe I was a little bit fast there. Getting a branching pattern is not that difficult. Mega every day does so many phylogenetic tree construction or branchings. But how do you know those branchings are the branching pattern is statistically supported? What is the chance of that particular branching pattern is because of a chance. Then you have to rule out the chance factor here, whether it is actually happening or it's because of the chance. It's all about statistics there. That those statistical analyses come under bootstrapping actually. This we will do. These are the whatever you see 100%, 98%, 70%. These are bootstrap values, and these are must. You should present these values on a phylogenetic tree. Otherwise, your reviewers will not accept your phylogenetic.
Excuse me, sir.
Yes, ma'am.
How to summarize this data? Means if you are saying 20,000 data are coming, then how to summarize this data? Is there any statistical software, or how to summarize this? If we are doing some research, how to conclude?
It's very simple, madam. What I gave is a very theoretical background, but when you do it in real life, in the sense when you download Mega software, all these things will be done in in 5 or 10 minutes, depending upon the data set. Actually, for example, I was telling you, if you use 10 sequences, you will get so many hundreds, thousands of distinct topology. The program will take care of it within a minute or two. Actually, the programs are powerful enough.
Yes, sir. I know that. I did. I have done that practicals, and Mega 6. I used Mega 6. But how to summarize? The data is very big, sir. So manually we will do, or any software?
No. See, if you have a multiple sequence alignment, what summary you are expecting? If you have a multiple sequence alignment, you feed it to the program. Program will give you a phylogenetic tree. That is a summary of the evolutionary relationships and the branching pattern and the bootstrap support, statistical support.
Oh.
What else you expect?
Okay. So phylogenetic tree is the summary of our result. But
yes,
it is showing a big result like gaps and what and links and all things, alignments.
Yeah, these, maybe if you go through the slides, I can and after this demonstration, you will have a better understanding.
Okay, okay.
Excuse me, sir.
Yes, ma'am.
Sir, my work.
Hello? You're muted, Meenakshi.
Am I audible, sir?
Yes, yes.
Sir, my work is on the family metaceae. I'm working on the family metaceae, essential oil. I extracted 10 essential oil from the family metaceae. So how can I get the data on NCBI? Because yesterday I have practiced by watching your video on Mega. Then NCBI I put the keyword metaceae. Then I get only 2 options on that. So how can I construct the tree for that data?
I think I am not very familiar with that particular. It's a plant. You are talking about a plant family, right?
Yes, sir. Yes.
Okay. I don't have much idea about plant taxonomy, but if I am a beginner, if I were a beginner in plant taxonomy and I would be interested in a family, I would go to the recent publication and recent in the sense last 1 year and use their sequences. You know, every study will have some sequences. You can actually go to that particular study and get all the information of the sequences they generated. And you can download all those sequences from GenBank.
I can download it from the paper?
Not the paper. You have to see what are the sequences they have generated during in their study, where they have deposited. And if they have deposited those sequences in NCBI, you can retrieve them from NCBI very easily. Or there are some certain websites which accepts the deposition of alignment files. So you can go to such websites and download this alignment files.
Okay. Thank you, sir. Thank you so much.
Thank you. Thank you.
Thank you, sir.
Hello. Any more question? I can. Ananya Sarkar, do you have a question? Ankita Sarkar, you have any question?
No, sir. Actually, the problem which I face when I'm going for multiple sequence alignment, when I take the sequences from NCBI, sometimes it says that there is error. So might be the sequences should be having some gaps, or because of that, I'm unable to generate that multiple sequence alignment file. I can generate it to cluster Omega, but on Mega, when I'm trying, I'm facing this problem.
I hope the direction is the same. Direction of the sequences is the same.
Sir, I don't have much experience handling sequences, whether I have to trim the
fine.
sequences or not. So that is the issue I face.
There could be many issues. One of these issues could be the sequence could be very divergent. Okay. Another could be the direction of the sequences. If you do reverse complement, you might get some luck.
So these are some fine tunes, which the more you work, I think more experience you have in handling the data. Thank you.
Yes, sure. Thank you. Any more questions?
Yes, can I ask a question, Dr. Shani?
Yes, please. Yeah.
Thank you. Does it make sense to build a phylogenetic tree to analyze evolution of genes between 2 or 3 strictly related organisms, like, for example, Homo sapiens and strictly related ancestors, to assist the conservation of those sequences? Or I have to extend also to other less related organisms?
I think it depends upon your question, research question, I guess. What are you trying to understand there, actually? If you are trying to understand the evolution within a group, okay, you get many sequences of that particular group and take a couple of sequences from related sister taxa, then you can make a phylogenetic tree. It all depends upon the range of your question, like how wide is your question, something like that.
Okay, so if
and I'm not into animal phylogeny, so I don't have much idea about specific ideas about these things. Sorry about that.
Okay, thanks.
Sir, good morning to one and all. So this is a very wonderful and great session for us. Actually, I am Dr. Rajaprabhu from KS Rangasamy College of Arts and Science in Tiruchengodu in Tamil Nadu. Actually, sir, I'm working in lichens. So last 5 years, I'm working in lichenology, especially the terrestrial and marine lichens. Actually, sir, we have a big clarification, and still the Indian people are lacking extracting the lichens DNA for the polymorphic DNA or else in the metagenomic DNA. So why this problem is came means it's a combination of organism of algae, bacteria, the major component of fungus. So in this case, we are focusing only the Ascomycetes and Basidiomycetes. So especially the endolichenic fungi like mucorales and many penicillium species have been described from us. But like in the case of the previous data which was supported and which was available in NCBI, so there only the Lecanarels genus only showing in the Ascomycetes group. Apart from that, Parmeliaceae also available there. But my question is, why only these two major fungal components will be there dominating in the other lichens, including the pinhead lichens. So you people are very aware about the Kulluhavu. I think in Telugu it's called Kalluhavu. So we will add into the making of biryani. So it is like look like the dried mushroom. So in this case, the fresh DNA and the herbarium samples DNA can be extracted from the plant samples and the fungus samples. So whether it may be the mushrooms also. But in our case, we are lacking in the extracting of the pure DNA because of the combination of different organisms. I already told you that algae, bacteria, and fungus. So here we need to standardize the protocol based on the domination of fungal component. But ultimately, we can't able to get. So will you please give some suggestions for the extracting the pure DNA from the microbiome?
Thank you so much. I thought there are two parts in this question. First one is a difficulty in extracting DNA, right?
Yes, sir. Yes, sir.
And second part is how to retrieve sequences from NCBI. Second part should be very easy, I believe.
Yes, sir. I can. Actually, your session was very nice. Nah? So earlier, we have submitted around 40 sequences.
Okay. So
only
sorry,
endolichenic fungi.
Let
Only
me,
the endolichenic.
so let me, I mean, about the DNA extraction, I don't want to get into that part right now. Let me focus on the analysis part. Okay. Thank you.
Okay. Okay.
I'll get back to you on the WhatsApp.
Yeah.
Group. Okay.
Sure, sir. I'll send contact with the mail. Thank you.
Okay. Harjot Kaur, do you have a question? No. Monica Thakur. Vishal Kumar. P. Vijay Sirivardhana. Any question you have? Okay, no question. Leeleshwar Kumar. Hemant, do you have a question? Dikshita? Vandana Sharma? Okay, let me take some questions from the chat box.
Hello.
Yes, sir. Yes, Hemant, yeah. Hello, yes, Mr. Hemant. Hello? Okay, fine. There is a question like which is the recent phylogenetic fungi classification? Please refer to Hibbett et al. 2007. Then you can refer to the follow-up publications. Jonathan Mang, is it clear? Give me a thumbs up.
Yes, sir. Thank you, sir.
Hibbett 2006 mycological research. You start with that, please.
Thank you, sir.
Parjot, which method is better, distance method, discrete method? Right? That's a very good question. It's a very commonly asked question whether I have to use neighbor joining, maximum likelihood, maximum Parseval's Bayesian. I think it depends upon your research question again and the amount of sequences you have generated and how big is the data set. We always start with neighbor joining, and if we have energy computational resources and expertise, we can go towards maximum likelihood and Mr. Bayes. I would all suggest do all these three: neighbor joining, maximum likelihood, and Bayesian. Bayesian is difficult to do in that, and it all depends upon your research question. If you are just reporting one fungal species from particular habitat, you want to just give the identification, then neighbor joining is good enough, I think. If you are reorganizing the whole fungal taxonomy, for example, then you might like to try all the tree building methods and tell that all the tree building methods are giving the similar kind of results. It depends upon the severity of your research question. Thank you.
Sir, excuse me, sir.
Yes.
Sir, for the beginners means if we focus on the one fungal genus and then phylogenetic tree constructed, or more genus, or the different groups, genus of different group, what will be the methods for beginners?
Beginners, I would say, you just, for example, if you have a fungal culture, just extract DNA from it.
Okay.
Then amplify ITS region.
Yes.
Okay. Then get it sequenced. Once you get the sequence, you get chromatograms. Okay. Start from the chromatogram. Okay. Then get a Quantix consensus sequence. Then do the blast of the Quantix consensus sequence. Get the homologous sequences from the GenBank. Then once you have a sequence once you have a data set, you do the multiple sequence alignment in the Mega software. Once the multiple sequence alignment is ready, you can construct different kinds of trees: neighbor joining, maximum likelihood, maximum parsimony in Mega software. It's quite easy to select the tree building methods in Mega. If you for a beginner, Mega would be the best.
Okay.
And start with simple things like one culture. If you are not,
Morning, sir.
Yeah, Vandana, yes.
Okay, sir.
Sir, I have a question.
Yes.
Actually, if we do the phylogenetic analysis in case of plants, then there is any criteria how to select the genes? Maybe chloroplast gene is better or the nuclear gene is better?
Madam, I'm not from plant taxonomy. I don't know much about the markers used, but I think it's more than one gene region, and you have to refer to recent publication about that. Actually, I'm sorry, I'm not into plant taxonomy.
Okay, sir. Thank you.
Thank you. Yes. See, I'm going to do a few things here right now. The first one would be to start with Mega. How to. If you are a beginner, I would suggest you start with Mega. For that, you need to go to Mega website and download it and install it and get the idea about the software. Let us do that. Is that okay? Give me a thumbs up. Okay. I'll be switching off my video to avoid distraction. Okay. Okay, do you see my Google page? Yes. Okay. So let me go to Google and type Mega software. Can everybody see the result page?
Yes.
Good. Thank you. Okay. It automatically, detects your computer setting. Mine is Windows, GUI, Mega 11 64-bit will be downloaded. I would say download. Then you just have a look at the agreement, user agreement. If you are interested, then you say accept. And as you know, Mega is free. So you have to give some information about it. I am from India. I am from CSIR NIO. I am a researcher. It is a research institute. Then I say download. It will take some time to download. Then I click on the executive file, exe file. Then do you want to allow this app from an unknown publisher to make changes to a device? Yes. English, yes. I accept the agreement. Next. Create a desktop shortcut. Yes. Create a quick launch shortcut. Yes. Please select the installation task that it should be performed. Check both. So almost installation is complete. Let us launch Mega. This is Mega. Can everybody see this?
Yes, sir.
Yes. So there are some important things you might like to know. First one button is align button. Second one is data button. Third one is models, distance, diversity, phylogeny. This is an important one. Here you can make different kinds of trees. Maximum likelihood tree, neighbor joining tree, minimum evolution tree, UPGMA tree, and maximum participant tree. And there are some more actually. Now this is Mega graphical user interface. So let us have some fun. I don't, assuming that you don't have any sequences of your own, you have not generated any sequences, but you want to have the fun of, get the fun of phylogenetic analysis actually. So what you do now, simple, you go to the example files, just select one of the example files. Okay, click on the example. Can everybody see these examples?
Yes, sir.
Yes, sir.
Good.
Yes, sir.
Yes, sir.
Good. So you take one of the Mega files. I will select the third file, command statements. So data set is open. Actually, there are some 13 sequences are there, some pathogens. You can see there are so many gaps are there. There's actually means these are constant characters. Let me color it actually. Color cells. Let's have a look at the tree, that alignment. This is a multiple sequence alignment. It's a ready-made multiple sequence alignment. Okay, is that clear?
Yes, sir.
It's ready-made one. Okay. Now what you do, if you are interested in constructing a neighbor joining tree using this data, a multiple sequence alignment, go to data. Not really, you go to file. go to phylogeny, sorry. Select construct neighbor joining tree. Would you like to use the currently active data command underscore statements? You say yes. Then here you have to make some selection. Test of phylogeny bootstrap method. Bootstrap method is the way you find out this, reliability of the branching pattern. How many replicates you want? Say 100. Remaining things you just leave at as it is, as they are. Then you say okay. So your tree is ready. Your phylogenetic tree is ready. Take one of these sequences, right click and root tree. So your tree is rooted and these are the bootstrap webs. Okay. Then you go to image, copy to clipboard, go to your Word file. You say edit paste. So your tree is pasted on with Microsoft Word file. You can use it in no publication. So you say the trees as test tree from example file. Okay. The poll is live. Please let me know, is this clear? There are 217 participants. I want the response from each of you. Please respond in the poll. Can you see the poll? Okay, there seems some problem. Anyway, now, and I'm ending the poll. Just reply in the chat box. Is it clear? Yes, if you have understood. No, if you have not understood. Let me just focus on the chat box. Okay, should be enough. I think most of you have understood. Anyway, let me repeat one more time. Okay. Let me go to Mega Software. Here are the example files. Ready-made multiple sequence alignment files and many more. Click on click on that. I will select the third file, command underscore statements. I open it. The alignment is open. Now I go to phylogeny. I say construct or test maximum likelihood tree or construct or test neighbor joining tree. I'll just go to likelihood tree this time. Would you like to use the currently active data? Yes. I will keep the test of phylogeny to bootstrap, number of bootstrap replication 100. I will not deal with other things right now. This is the maximum likelihood tree construction. So it is taking more time because ML's maximum likelihood is more computer intensive or resource intensive actually.
Sorry, sir. How do you choose the number of bootstrap?
I mean, it's better to start with 100. And if you want to more accuracy, maybe go to 500 or 1000.
Okay, thanks.
And here our tree is visible. I'll take one of these as for the outgroup. I have no idea about this, the background of these sequences, but I will take one of the Paris one. And I just right click on it and root tree. And I go to image, copy to clipboard, Word. And I paste it here. So right, your tree is here in the Word file. And here is your scale. And I will save it as test tree from example file ML maximum likelihood. Okay. Give me a thumbs up if you understood. Now, if you did not understand, just type it in the chat box, no.
Sir, I have a query. Am I
Yes.
audible?
Yes, yes.
Sir, do we always need to start with 100, like bootstrap number 100, or sometimes we can write less than 100 or more than 100?
My experience tells me if you are doing maximum likelihood analysis and you have 500 sequences in the data set, you start with 50.
Okay, so sir, which kind of difference will be there in the tree if we will put the number less than 100 or more than 100? Can you please demonstrate in this by using this example?
I hope there won't be much difference actually.
Okay, so please elaborate it or demonstrate it.
You couldn't see on the tree actually. You know, maybe there is a difference of 1 or 2%. That's it.
Okay, fine. Okay, thank you, sir.
Okay, I think some people have some questions. Okay, Raja Prabhu. Dr. Raja Prabhu.
Yes, sir. I'm here, sir.
You have any question?
No, sir. Now I don't have any question.
Okay,
Session was already wonderful.
Okay, thank you.
I'll let you know.
Okay, Dhanush Begur. You have any question? Okay, because you have raised your hand. Mohan Galande, you have any question?
No, sir. Yes, sir.
Okay, fine. Rebecca, do you have any question? No. Okay, fine. Good. Looks like people are happy. Jane Mary.
Yes, sir, they're happy.
Jane Mary, she's asking how to construct trees using multi-genes. Okay, we'll do that later, maybe in a different session, separate session. Okay, Vinay, you have any question, Vinay?
Yeah, good morning, sir.
Good morning, yeah.
The demonstration that you did was a need sequences. Now, sometimes when we download the sequences from NCBI, they are of varying lengths. Right. So we trim some sequences and then we construct the phylogenetic tree. Can you just give one example, or we can have that session later?
That is in the plan. Vinay, that is in the plan.
Thank you, sir.
Yeah. Kavita? Kavita Wak, do you have any question? Okay, lower. Fine. So as Dr. Vinay suggested, and Dr. Hari, you have any question?
Good afternoon, sir.
Yes.
It's nice having basics again. Sir, I'm just wondering, like, you'll also be demonstrating the RAXML GUI now?
Yes, I have just started with Mega. Let me now go to NCBI and get some sequences. Let me show how to get to homologous sequences for an already existing sequence in NCBI, for example, Aspergillus niger. Then after that, let me show how to edit the labels in Microsoft Word. Then do NG tree or my maximum tree in Mega. After that, I'll go to RAXML and I'll show. RAXML will take only. Hari, can you mute yourself?
Yeah, thank you.
RAXML will take only 5 or 10 minutes. Okay. Thank you. Now now you know how to make a tree from an example file. Okay. I am a beginner. I don't have my own sequences, but I want to get some sequences from GenBank and I want to construct a phylogenetic tree. What do I do now? I go to Google first, then type NCBI GenBank. I go to GenBank overview. Then I type Aspergillus ITS. Aspergillus niger is the name of the fungus. ITS is the gene name or gene region actually. Then I would say I want the sequence from type materials. It's a taxonomic concept. Ignore it if you don't know it. So then I'll go and say search. So this is the suggestion given by the NCBI itself. Okay, let me see the FASTA file of FASTA format of this. This is how the sequence looks. Okay, here is an accession number, is a species name, is the culture number, and the gene region. And it also gives additional information saying this is from the type material. So either you go back, then you say BLAST. Okay, folks, please focus on the demonstration. You ask me the question once I'm done with the demonstration. Thank you. Okay, so here is the accession number automatically copied. I'm going back. I'm going back to the first step. I'll type Aspergillus niger ITS type research. Then you have the sequence suggested by the NCBI itself. Then you say BLAST. Here the sequence accession number is automatically copied, and you have to keep some of the default settings. Maybe you click on sequences from type material and optimize for some more similar sequence. BLAST M. You do BLAST. Okay, once select, then you go just 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Just select first 10 news, just select, just for fun. Okay, then you go to download. Then you say download FASTA aligned sequences. So here are your sequences. Make sure you copy this to a Word file so that you can edit better. Copy, Word, paste it. You can reduce the size. Make sure you add the query sequence also here. I think this is already there. So 16888, this is already there, therefore no need to add. Okay, then you need an out group. So you search for Aspergillus flavus ITS region. Select the FASTA format. Copy this. Paste here. It doesn't matter which font you are using, just for the consistency I am using this. You don't want to show all these things on a tree, you will need to edit the labels now. Before that, you save the file. My Aspergillus niger data set. Let us start editing it actually. You don't have to mention point 1, just remove point 1. You don't have to say ITS region because it's all are from ITS region. You just say, you don't have to say type also, all are from the type. Okay, second one. You don't have to mention all this information. information. Same here.
आउटगोइंग वालों से लेने नहीं चाहिए।
Any problem there? Make sure there is some space here. Enter button is there. Here actually. Okay, save it. Now what you do, select all the sequences. Select all. Then you copy. Now open your Mega. Say align, edit and build alignment. Create a new alignment. And you say, okay. Are you building a DNA? Yes, DNA. And you say edit, paste. The last one is unwanted, just edit, cut. Now select all sequences. Then you go to this align using muscle algorithm. Align DNA, and you say okay. So here is your multiple sequence alignment. This is your output taxon. Anyway, you can delete this initial 3. You can just select all these and just say edit, cut. Here also select all these things. We say edit, cut. Maybe you add question mark here for the missing, only at the beginning. Now you save this file, data, export alignment as faster. My Aspergillus niger data set in the FASTA format. Okay, now minimize this. Go to phylogeny. You say construct maximum like or the construct neighbor joining tree, for example. Or you can just say data phylogenetic analysis. Protein coding, no. Minimize phylogeny, construct or test neighbor joining tree. Would you like to use the currently active data? Yes. Test of phylogeny is bootstrap method, bootstrap replication. Let me make it 1000. The things will remain same. Let us keep it as per the default setting. Here is your neighbor joining tree ready. So flavors, click on it, root tree. You can hide values, bootstrap page values less than 50. Maybe 0.05. These are bootstrap values. It can be converted into percentage. I'm just struggling to find where is that option. Maybe later I'll find out. Anyway. Okay, I fixed it. I have hidden the branch length. It was actually confusing. So this is the phylogenetic tree. Okay, now you can save the current session. My Aspergillus niger tree. Now I copy this image, copy to clipboard. Open a new Word file. Paste it here. You can actually edit these labels, you ungroup it. You just say Aspergillus niger, italics and bold if you want. Okay, here is your phylogenetic tree with bootstrap support and all. So these are the bootstrap support percentage. Okay, you can save as desktop. My Aspergillus tree in Aspergillus niger tree in Word format. In Word format. If you want to know the information about the tree, you can go to display caption you can go to caption, display caption in your window. You can just copy all this information and put it in your paper. Is this clear? Oh, I cannot repeat. It will take half an hour more. No, I cannot. You just look at the video of this later. Thank you. Okay, Ashwini, what is your question?
So how to decide whether to use neighbor joining method or maximum likelihood method?
No, there is no decision as such. You just start with neighbor joining, then you go towards some more sophisticated methods like maximum likelihood Bayes, and you can always start with neighbor joining because it's easy to do. You'll get, when you do a neighbor joining tree, you get a rough idea about it.
Okay. Thank you.
I have Ashutosh already answered that question. Arjot, you want to change the tree? Okay, let me see. Okay, you. Did you see this? Arjot, did you see that?
Yes, sir.
You can change. Any question? And how to decide whether how to decide the out group, right? There was a question, right? What are the important parameters we should fix while constructing any tree? I think it depends upon the sophistication you want. If you're a beginner, you just look at the, you just select you start with neighbor joining, then you bootstrap analysis of maybe 500 replication or 1,000 replication. If you want more sophisticated one, then you may need to select some DNA substitution models, especially for maximum likelihood methods and Mr. Bayesian method.
Yes, sir, I am listening. Once we select any method, then in the left side, whatever panel is coming. So I'm talking about the branch length. You selected some parameters over there, and then frequency, statistics. So in that particular things, how to change the numbers, what will be the effect?
Okay, I'll show you. Okay, yeah.
Okay.
Let me go back to Mega now.
Fine, sir. Thank you. Sir, please, could you please repeat once this one circular one actually?
Yes, I will do that. Okay.
Right, thank you.
Please don't put any questions in the chat box unless and until it is very critical. Okay, because when I get a beep sound, I have to get back to the this tab. Please, thank you. See, I'm closing Mega discard results. RBA on yes. No. So this is a tree file. Okay. Yes, go here actually. What kind of flow you want? Traditional, radiation, circle. Is that clear, Ashwini? Ashwini, is this clear?
Yes, sir.
Not Ashwini, I think. Aarti, you asked for it, right?
Yes, sir. It's clear. Got it.
Okay. Okay. Let me spend more time with Mega now. Maybe 5 more minutes. Okay. Discard results. Look, here is my FASTA file. Okay, FASTA format. Align or analyze or align file. I think it's already aligned, so I will analyze. Sorry. Analyze. So before, let me just start with how to make a maximum likelihood tree. Go to phylogeny, construct, test maximum likelihood tree. Would you like to use the currently active data? Yes. Test of phylogeny, bootstrap method, number of replicates is a maximum likelihood. I'll just reduce it actually. Okay. Model used, it says Chimera 2, default model given is Chimera 2 parameter. Okay. You can change it for maximum likelihood. Let us keep it and gamma distributed or whatever. There are under gamma rate among sites, you have uniform rates, gamma distributed has invariant sites, gamma distributed, blah blah blah. These are most complicated, more complicated stuff. Just don't touch it right now. So this is the maximum likelihood tree. You can load it. Okay, these are the bootstrap values, and we used Chimera 3 parameter model as suggested by the software. You can find out whether that model is correct or not. For that, you go to models, find the best DNA model actually. Would you like to use the would you like to use the currently active data? Yes. You just accept all the default settings. But according to this model test, the model is T92. T92. What is T92? T92 is Tamura 3 parameter. So we have to change the model. Okay. And finding it difficult to get it again. Wait, let me do the modeling. T92 is the model. No gamma distribution, no invariable, just T92. Okay. Let me go to phylogeny, construct test maximum likelihood tree. Would you like to use the currently active data? Yes. Bootstrap method? Yes. 100 replication? Yes. I'm going to change the model. I think Timura 9 model 92, I think this one. Timura 3 parameter model. Not gamma distributed, uniform rates. Okay. This is the tree when you use a different model actually. I don't think there's much, I don't think there are many differences. It's because it's a very small tree. Okay.
Okay, sir. Okay. Fine.
I'm discarding the result. Okay. Is this clear?
Yes, sir. Yes, sir. And I think the things will be fine when we will do more practice on this. Okay, thank you, sir.
I'm asking the audience, is this clear?
Yes, sir.
Okay, great. Now,
Yes.
now we'll have some more fun. Actually, we'll just download RaxML and just make phylogenetic tree. Okay. For that, we'll go to Google, then type XML DUI. We just download. More info. Run anyway.
Sir, hello.
Yes.
Yes, sorry to interrupt you. Before moving to the RaxML, there was a question in the chat box. I think we missed. Can we make the phylogenetic tree for by using one gene or multiple genes? Like it is for how can we construct the tree by using if like I'm having a single gene and I have 10 sequences. So is it possible to make a tree, or I have 3 different genes and I have 12 or 50 sequences, suppose. So is it possible to make a phylogenetic tree? There was a question someone asked, actually I can't scroll.
Yes. We will discuss that. Yes, we will. Just let me just show the RaxML thing. It's a very simple program. It's a simple looking program. This is to make a maximum likelihood tree, especially when you have a large data set. See, you remember we created a FASTA file, right, of our Aspergillus niger data set. Okay, we will use that, and you just say load alignment desktop my Aspergillus niger data set FASTA format. This will be using a copy of your input file because there were some issues. Okay, I mean, you just see the issues, blah blah blah, close. Then you say run. It's running. Calculation is finished. So found one tree. So now we have to go to desktop. Then we have to check for this file, RaxML best tree.myaspergillus. So RaxML best tree. This is the file. You can directly open this in Mega actually. This is your maximum likelihood tree using RaxML. You can outgroup it. Since there is some difference in terms of, the branch length of the outgroup. Now, is this clear?
Yes, sir.
Okay, great. Now, coming back to that question, can we use more than one gene region? We can. Researchers have been using it actually. I'll just give an idea, I'm not going to demonstrate it. Let me just open the FASTA file, that Aspergillus. So this Aspergillus flavus ITS region, right? For these many ITS region for 11 sequences. After this, you can paste the beta tubulin if you want. And you can add one more after that. Then you do the phylogenetic analysis. But for each gene region, you can have a different model. It's a little bit complicated. I'm not getting into it now. And we will have a separate session on that. Is this clear?
Okay, sir.
Okay, now I'm done with all the demonstration. Let's have some discussion. Okay, maybe some of the doubts will be clarified. Tatasre, yes.
So my question is that how we decide using of number of bootstrap replicates, whether it is 100, less than 100, or more than 100.
No, I mean, it depends upon the size of your data set actually, and the type of tree building method. If you are doing neighbor joining, even if you use 1000 sequences, a tree will be done in half an hour or maybe 1 hour. But if you use a maximum likelihood method, if you have a slightly large data set, then it will take hours and hours. In that situation, if you opt for 1000 bootstrap replicates, it will take 2-3 days. I'm just exaggerating, but it will take lots of time. In case of maximum likelihood, you start with the 50 if the data set has more than 100 sequences. If it is a small data set, 100 is enough actually. Once you get a rough idea about the tree topology and the branch length, if you want to be perfect, you can always redo the analysis with the higher bootstrap or replicates. Is that clear?
Okay, thank you.
Yeah, thank you. How to prepare data set for multi-gene phylogeny? Masood, I think I have given some idea, but I'm not going to demonstrate that right now. Sir, which will be more accurate to use in publication, tree built from Mega or Rexem? I mean, Mega was not very popular among the publishers, especially peer reviewers. Now they are accepting it. For neighbor joining, Mega is okay. For maximum likelihood, better to use RaxML and other things. Ambikesh. How to go about data trimming, sir? I have given some idea. In the Mega itself, you can select a portion and cut it actually. If there are some gaps, you give question mark at the beginning and question marks at the end. But don't give any question mark if there are gaps in between. Those are genuine gaps. Those are evolutionary gaps. Have I answered it correctly, Dr. Vinay? This link will be deactivated after 10 minutes, okay? I think editing trick can be done in Mega, also in Fig Tree, and probably many more are there actually. And you can copy it to PowerPoint presentation and you can edit it there. You can color it, whatever you want. Yes, the session is going to end in 10 minutes. Just submit the feedback, using that feedback form. And if you don't submit the feedback, you will not get the certificate. And people who have just attended, people who are just logging in, they will not be allowed. For phylogenetic and bacterial strain, which sequencing should be done? For bacteria, you start with 16S rRNA gene. I mean, rRNA gene is equal to 16S rRNA DNA. Okay, that is the thing. From a large FASTA file, how can we make the phylogenetic effort difficult site of bacteria? I think if you have a large FASTA file, no, I am not sending the feedback to the respective email. No, I'm sharing it here and I'm going to close it right now. Because there are some 1,500 people who I don't want them to submit the feedback form without attending this. Thank you.
Thank you, sir, for your wonderful session and practices.
Thank you.
Excuse me, sir.
Yes.
So, at what percentage of similarity can you assign it to be a particular species? Like, is it is there a cutoff value for ITS? Like, say, 98%?
No, I think there are two things. One is sequence identity and homology, right? Sequence identity, you don't apply it to fungal actually. No. In bacteria, they had some, cutoff value. I think now they are very doubtful about such things. Identity just based on sequence identity is not really good. You need to do phylogenetic reconstruction and place it on a tree and identify it.
Sir, during our work, we found that I'm working on Eve. So we had done ITS sequencing. Sometimes when you do this mega and then you construct a phylogenetic tree, sometimes a genera from another clade comes into a totally different clade. So is it possible or is there some kind of sequencing error there?
Maybe that if the sequence is from GenBank, maybe the sequence was misidentified or incorrectly identified. How do you say? The poor labeling actually.
Okay, sir. So there is no definite cutoff value for in the case of ITS, right, sir? So if it is showing, say, around if there is 100% sequence coverage and there is around 97% similarity, we may assign it to the same species.
That's very that's oversimplification of the identification process. It is not so easy.
Okay.
People get fooled by such things. No, it is not in fungi.
Thank you, sir.
Thank you.
Can I talk, sir?
Yes, please.
Yeah. So follow-up question for that. Are there any resources to read up speciation of fungi with respect to current rules?
I didn't get it. Can you repeat the question?
The last question was, is there any cutoff to call it a new species? So the answer was that it's not that easy. So what are the resources to understand the current rules for speciation of fungi?
See, there is nobody gives any rules. Okay, every taxonomist is entitled to come up with his own classification. Okay, but the general acceptance is that it cannot be just based on some cutoff percentage, at least in fungi. You have to first make comparison with the type material. Comparison can be in terms of morphological characters, or it can be in terms of morphology plus other characters, maybe DNA sequence data. Morphological characters, if you have very clear distinguishable characters, that's a very good evidence that it's a different species or a new taxon. Okay, but if it moves towards the DNA sequence data, then you may try with one single gene region. Then we go for multi-sequence data sets. Actually, if the group is not well studied or group is not very much settled, so it's all about your hypothesis. Every new species is a hypothesis. So there are no rules set, but you have to develop your own convincing arguments in support of your arguments and data in support of your new species. Thank you. Vinay, am I clear?
Yes, sir, clear.
Yeah, thank you.
Excuse me, sir.
Yes.
Actually, sometimes we get sequences whose e-value is not exactly 0. So is there a way we can improve the quality of those sequences?
What value?
E-value. When we blast those sequences, we don't get the e-value of 0. So
Mhm.
is there a way to improve those sequences, to improve their quality?
I mean, you can resequence it and probably exclude the initial portion and the last fag end portion. Other than that, I don't think there is any way to you can improve the sequence quality.
Sir, sorry, you were not audible. Can you please repeat?
Your question was how can we improve the quality of the sequence? I meant to understand
Yes, sir. Yes, sir. Yes.
if the sequence quality is already bad, then you can resequence it, right? And when you do the blasting, you can remove some ambiguously or some regions poorly, some initial part that you can exclude while doing blast. But it also depends, even same for the fag end of the sequences. You can remove some of them when you do the blast. It also depends upon how many homologous sequences are there in the database for your query sequence.
Okay, sir. Thank you. Thank you.
You have 3 more minutes to submit the feedback.
Sir, can we also contact with you in future?
What is that?
Can we contact to you in future regarding any query?
The WhatsApp group,
WhatsApp
are you in the WhatsApp? Are you in the WhatsApp group?
Yes, sir. Yes, sir. Yes, sir.
It will be active forever. You can contact me there.
Okay, sir. Okay, sir. Thank
You
you.
you had some questions, right, Shashank?
Yes, sir. Can we make a phylogenetics through FASTA-Q file directly?
Yes, I think we had on FASTA format here, right?
I have a large FASTA-Q file, but we are unable to make our phylogenetics.
I have not done.
For a particular type of bacteria.
Let us discuss the case individually, P2P.
Okay, okay, sir. Okay, sir.
Kavita, what is your question?
Yes, sir. After completing the tree, preparing the tree, how to explain this tree?
Explain the. No,
yeah.
Okay. See, there are tree description is there, right?
Yeah, yeah.
Okay, let me open the tree file. Okay, user trees, analyze or open tree session on desktop. My Aspergillus tree. Okay, here you go to caption. Okay, go to display caption new window, and you copy all this content and paste it below your tree.
Okay.
This is that's about the the methods used to generate the tree, construct the tree. Okay.
Yes, sir.
And how do you explain the tree? It's a different ballgame.
Okay. Okay, sir.
Basically, you have to say my sequences are different in terms of branch length, and they are statistically highly supported. That's it. These are the only 2 things you can tell. And you can say if it is a taxonomic study, I have used the sequences from the type materials. That's it.
Okay, sir. Thank you.
Can you provide the WhatsApp group link? Okay, one of you can share the WhatsApp group link or email me. I will send you the link. Email me your query to contact. I will send the WhatsApp link. Okay, I'm deactivating the feedback form. I hope everybody submitted the feedback. Everyone submitted feedback.
Thank you, sir, for your informative lecture.
Thank you. Thank you so much. We will be in touch on the WhatsApp group.
Yes, sir. Yes, sir. Sure.
Thank you, sir.
Thank you. And you will get the certificates. You will please note that the organizer from the Holy Cross College has informed me that all will be, people who have submitted the feedback will be given a certificate. But this might take some time. They will take some 15 days. Okay. So please don't send me messages asking for certificate.
Hello?
It will take 15 days.
Okay, sir. Okay, sir. Have a nice day, sir.
Thank you, sir.
Thank you.
Have a nice day.
Thank you. Thank
Thank
you.
you, sir. Bye. Have a nice day.
Hello.
Thank you,
Thank
sir.
you for a
Very nice.
wonderful workshop.
Thank you,
Have a
sir.
nice
Thank you,
day.
sir.